All right, let's jump in. We're going to start with the chaotic, random bounce of a single, tiny atom and see how that simple idea scales up, way up, to a law that governs everything from the air in a tire to the very heart of a star. We're talking about the ideal gas law.
So here's a question for you. What could the air you're breathing right now possibly have in common with the unimaginably hot, dense core of a star? I mean, one is cool and all around us. The other is, well, it's a star. But the answer, believe it or not, lies in the same set of simple rules that govern countless tiny particles. And by the end of this, you'll see exactly how they're connected. Okay, first things first, we got to talk about pressure. You know it, you feel it, but what is it really? On a microscopic level, it's nothing more than a constant, relentless storm of tiny particles smashing into a surface. To really get what's going on in that storm, we need to zoom way in and just look at a single particle.
That's right. To understand the huge, macroscopic idea of pressure, we're going to shrink ourselves down and tell the story of one single, lonely atom, trapped and just bouncing around inside a box.
So here it is, our hero particle. It's got a mass, m, and it's zipping along with a velocity, vx. It's just moving, doing its thing, and over again it smacks into the walls of its container. And these little taps, these seemingly insignificant bounces, they are the absolute key to everything.
So let's build this up logically. Step 1, the most basic fact imaginable, our atom is moving. It's got velocity, which means it has momentum. Simple enough?
Step 2, because it's stuck inside this box, it can't just go on forever. Sooner or later, boom, it's going to hit a wall. Now, when it hits that wall and bounces off perfectly, its direction completely reverses. And in physics, if your direction changes, your velocity changes. And if your velocity changes, that means your momentum has to change too.
And right here, this is the crucial link. One of the most fundamental ideas in all of mechanics is that a force is just a change in momentum over a certain amount of time. So that tiny little bounce, that little reversal of direction, it actually exerts a real, physical force on the wall. And there it is. That's the final connection. That tiny force from one little collision spread out over the area of that wall, that is pressure. Now just imagine, not one atom, but trillions upon trillions of them, all doing this constantly, all at once. The pressure we feel every day is just the grand total of all those tiny atomic shoves.
Okay, so describing one particle is one thing, but how in the world do we scale that up? I mean, we can't possibly keep track of the trillions of atoms in a real gas. It's impossible. So instead, we need a set of rules, a kind of statistical model to predict how the whole swarm behaves together.
And those rules have a name, the Kinetic Molecular Theory. Let's walk through the assumptions. First, we pretend gas particles are just tiny dots, so far apart that their own size doesn't matter compared to the container. Think a few grains of sand in a giant football stadium. Second, they just move randomly in straight lines until they hit something. Third, and this is a biggie, we assume they totally ignore each other. No attraction, no repulsion, they just fly right past one another. Fourth, every collision is perfectly elastic, like ideal superballs. No energy is ever lost. And finally, we get to the most important rule of them all. That last rule is the real game changer. It's what allows us to build this incredible bridge between two completely different worlds. The invisible, microscopic world of jiggling atoms, and the macroscopic world of things we can actually see and measure, like temperature.
So get this, because this is the crucial point. Temperature isn't just some number on a thermometer. It is a direct measurement of the average kinetic energy of the particles. It's a measure of how fast, on average, they're all jiggling around. So when you heat a gas up, what you're literally doing is making its atoms move faster.
And when you take the pressure from all those collisions we talked about, and you combine it with this new understanding of temperature and all the rules of the kinetic molecular theory, you get this, the ideal gas law. PV equals NKT. Pressure times volume equals the number of particles times a special number called the Boltzmann constant times temperature. So elegant. And this isn't just some random formula you memorize for a test. As the source material beautifully puts it, this equation is a fundamental bridge. It lets us use simple things we can measure in a lab, like pressure and temperature, to understand what's actually going on in that invisible, chaotic world of atoms. Now this is really cool. What you're seeing here shows that the ideal gas law isn't just a flat equation, it's a map, it's a landscape. For any ideal gas that's settled down into a stable state, its combination of pressure, volume, and temperature has to lie somewhere on this surface. This surface literally defines all the possible states that gas can exist in.
So far, we've been talking a lot about average speed. But let's be real. In any group, not everyone is average. In any gas, you've got a whole distribution of speeds. Some particles are barely moving, some are going incredibly fast, and most are somewhere in the middle. And it turns out, this range of speeds follows a very specific, very predictable pattern.
This really shows that there's more than one way to think about the speed of a gas. First, you've got the most probable speed. That's the peak of the curve, the speed that the largest number of molecules have. Then there's the average speed, which is just the simple mean. And finally, you have the root mean square speed. Now that one might sound a little complicated, but it's the most important one for us, because it's the speed that connects directly back to the total kinetic energy of the gas, and therefore its temperature.
Okay, now we have to talk about the most important word in the name of this law: ideal. This whole beautiful, elegant equation is an approximation. It's a perfect model of a simplified reality. It works so well because of those assumptions we made earlier, but those same assumptions are also its biggest weakness.
Our ideal law is fantastic when gas particles are hot, fast, and really far apart from each other. But what happens if you start to cool a gas down and really squeeze it into a tiny space? Well, our assumptions start to fall apart. The particles get so close together that their own volume actually starts to matter. And those tiny little forces of attraction between them, the ones we ignored, they start to take over, making the particles want to clump together. Reality, as always, gets a little more complicated.
And that leaves us with one last fascinating question. We've just built this perfect, elegant model for an imaginary ideal gas. So what happens when a real gas gets pushed to its limits? When it gets cold and dense and messy and just stops playing by those ideal rules? Well, that's when it starts to turn into a liquid or a solid. And that's where physics gets even more interesting.